So I'm here, and I thought it would be useful because at the end of a few days, you're mentally exhausted, and I thought I would do something with no content, or maybe not, or just at least something different. I'm not obviously involved directly in artificial intelligence or singularity ideas, but I thought I'd talk to you about what our current picture of the universe is and how it's changed our picture of living systems in ways that relate to information processing, actually. And so there is some, I thought I could say something was actually relevant, otherwise I wouldn't have agreed to come. And you can decide. So anyway, the short version, which I sort of said a little bit in a different way when on the panel, the short version of what I'm going to talk about was based on a graduation address at a private girls' school. Now, I've given 2 commencement addresses in my life so far, and I've never had the guts to say this. Some people say it was Kurt Vonnegut. I'm not sure. I don't think so. But he began by saying, things are going to get unimaginably worse, and they're never, ever going to get better again. So that's the short picture of what I want to convey. And so the summary is that the universe we live in is probably the worst of all possible universes for the quality and quantity of life, as you'll see in the long run. I'm talking in a cosmic sense now. Cosmology, as I'll point out, at least as we now know it, will end. Life will end. Maybe the singularity will be hidden if there is one, as I'll try and point out. But I'm optimistic, so diamonds are forever. Okay, so that's where I'm going to head. So what I want to do, before I can talk about the future, as I tried to indicate, it's actually a good idea to be able to make, if you're going to make predictions, thank you. Is this in your way? Good, time to leave. If you're going to make accurate predictions of the future in any way, it's a good idea to know what the present is. So what I want to do, since I actually think the future is fun to talk about, but as I pointed out, not necessarily worth much, I want to just explain to you what we've learned in the first 10 minutes of this, because the universe is crazier than we could have imagined. Again, a point I made. We didn't come up with a picture of the universe by pure thought, because all of our pure thought, for the most part, was well, not, if not wrong, in the wrong direction. So, here is a picture of part of the universe. And one of the big questions, if you're worried about the future of the universe, since Einstein tells us that essentially gravity is the dominant force on scales larger than humans, is, I was going to have slides on this, but you're all a well-educated audience, so I don't have to tell you that the universe is expanding. And Hubble discovered this, and so we've discovered the universe is expanding, and the big question of 20th century physics became, what will the expansion end? Is it going to stop and recollapse? And general relativity tells us that, in fact, that's determined by the amount of matter in the universe, because matter produces gravitational attraction. So one of the ways to determine the future, and the reason I got into cosmology, in fact, was because I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And then that's from a basis in particle physics, because I wanted to know how much stuff there is in the universe. And it turns out you need particle physics probably to know how much stuff there is in the universe, but we can actually weigh the universe. If we want to determine the future, weigh the universe. Now, how to use the weigh the universe? Well, you stand on the shoulders of giants. In this case, a bunch of gravitational giants, and in this case, Einstein. Here's a picture which is worth 1,000 words. This is a picture of a cluster of galaxies. Clusters of galaxies are the largest bound objects in the universe. And they, therefore, if you can weigh them, you can weigh anything, because anything that could fall into anything will fall into a cluster of galaxies. We're a part of a cluster of galaxies called the Virgo cluster of galaxies. And they're about, 8 to 10 million light years across. They're huge. And this picture is a fascinating picture, because every dot in the picture is not a star, but a galaxy. Of the 400 billion galaxies we know of in the universe. So every one of these galaxies has maybe 100 billion stars in it. And this cluster happens to be located 5 billion light years away from us, speaking of long-lived civilizations. So that means the light from this cluster left 5 billion years ago. that we measure today. And that means among those hundreds of galaxies with hundreds of billions of stars in them, there could have been civilizations that are now long gone, because in fact, most of the stars in this picture don't even exist anymore, because it's 5 billion years old. The light was emitted before our sun even formed. Okay? So those are those are the things that I find inspiring at some level. But in any case, we can use this picture because you don't have to be a rocket scientist to see something strange about it. And that is that there are these weird blue things that are different color and shape than the other things. And what they are is a manifestation of something that Einstein first predicted, but he said would never be important because he didn't understand astronomy. It's true. It's something called gravitational lensing. Einstein told us that mass curves space, and it does. And that means that if you have a large enough mass distribution, you could curve space, and if you have a light source behind that mass distribution, the rays from the light source can go around, come back, and be focused, like my glasses focus things. So you can magnify images behind an object by the curvature of space. Space can act like a lens. Or like a cut glass goblet or something irregular with holes in it. If I look through here, I might see many copies of you. That can also happen. And this is exactly what this picture demonstrates, although Einstein said it would never be measured. Here it is. These blue things are multiple images of a single galaxy located 5 billion light years behind that cluster. So it is that galaxy, which would not be visible if it were not magnified by the curvature of space, is also split into many things, so it's distorted. All of these images are images of the same object. It's remarkable. But as remarkable as it is, what's more remarkable, of course, is we understand general relativity. So it is a computationally difficult problem, but one that is doable, to invert this image and say, where is the mass that would determine the image? Because the mass produces the lensing. So we could try and ask, where would you have to put massive objects, and how much mass would they have to take the light rays, and you do ray tracing, which you could do in computers, and many of you are familiar with. And you ask, where's the mass and how much of it must there be in order to produce that image, and we can do that. And so here's the inversion. And you see in this image, the spikes are where the galaxies are, that's what mass is. But you'll notice that most of the mass in this object, in this cluster, is where the galaxies aren't. 20 to 40 times, well actually 40 times as much stuff is in the system as is shining. Most of the mass of this system, as most of the mass of all systems, is dark. And physicists, with their linguistic perspicacity, call that dark matter. And we also know, for reasons I will not go into in this lecture, is that this stuff cannot be made of protons and neutrons. We are virtually certain of that. It cannot be made of the same stuff that makes you and I up. It must be some new type of elementary particle. And in fact, let me just skip this for a moment because I think I have an image. We can actually do experiments because that's where we learn things, not from theories. And here's an experiment which actually I proposed 25 years ago, I guess, that is now the basis of most dark matter detection experiments. It's you just cool a blue. This is very computer-centric. You take a germanium wafer, which you can produce cheaply with high purity because of the computer industry, and you cool it down to 1/1000th of a degree above absolute zero, and then and you put it deep underground in the dark matter particles. The great thing about this is, you see, if the dark matter is not made of planets or large gas clouds, which it isn't, if it's made of elementary particles, new types of elementary particles, then it's not just out there, it's in this room, going right through you now. And that means we can do experiments on Earth to detect it. And so you put these underground to shield you from cosmic rays, and you get lots of particles that are going through here. Most of them go right through the Earth without knowing it was there, we think. These are the particles we think make up dark matter. But every now and then one may bounce off this germanium and heat it up by 1/1000th of a degree. And you can measure that. And so that's a way to detect. So these kind of detectors are built around the world and are currently operating and haven't yet detected dark matter. But the point is, it doesn't matter what it's made of. We can weigh it. We can ask how much dark matter is there, and therefore how much stuff is in the universe, and we come up with a result which in principle answers the holy grail of physics, that since I've been around, which is what's the geometry of the universe? Because Einstein told us that the universe, matter, curved space, and it turns out the universe can have one of three different geometries. Three-dimensional curved geometries, which you can't picture in your mind, but you can write down mathematically. We open, closed, or flat. And in such a universe, a three-dimensional curved space would be, while you can't picture it easily, would be one in which if you looked far enough in that direction, you would see the back of your head. Because space curves on itself. Open universe is infinite, and so is a flat universe. But as nice as that is, what we also have been told is that if matter dominates the universe, then a closed universe will expand, stop, and contract into a big crunch. An open universe will go on expanding forever, and a flat universe is the boundary between them. So that's why we wanted to know what the geometry of the universe is, or why I did, because then once we knew whether it was open, closed, or flat, we know the future. So we've answered that question apparently with this, because we can answer it. And in physics, whenever you have important quantity, you give it a Greek letter. So we call it omega, to sound good. And the omega is the ratio of the total amount of stuff in these systems divided by the amount you'd need to make an exactly flat universe. So omega bigger than 1 is closed, omega less than 1 is open, and omega equal to 1 is flat. And apparently we answered definitively that the universe is open. About 10 years ago. This is about 12 years old, this bit of data. The problem with that is that theorists like me knew that was wrong. Because the only mathematically beautiful universe is a flat universe. And then observers were coming up with the wrong answer. Now, the problem is that, well, there's clearly one problem with this, is that it's very indirect to measure the mass and use general relativity to determine the curvature and determine the curvature. Wouldn't it be better to determine the curvature directly? And that's the next result I want to show you. Amazingly, we've been able to measure the curvature of the universe directly by using a simple fact. So here are two-dimensional images of two-dimensional curved universes. I remind you, our real universe is three spatial dimensions, so a flat universe doesn't mean flat like a pancake. Rather, you can see from the drawing of triangles on this that a flat universe, a triangle is a triangle in two dimensions, but on the surface of the Earth, a triangle, the sum of the angles can be greater than 180 degrees. In fact, on the surface of the Earth, you can draw a triangle where you go on the equator up to the North Pole and back down to the equator with three 90-degree angles. I say North Pole because I'm northern hemisphere centric, but you can do the same thing for the South Pole. And so you get 270 degrees. That would tell you that the Earth is curved, even if you couldn't go around it. And an open universe. So it turns out that this two-dimensional intuition, or mathematical intuition, is actually accurate in three dimensions. Namely, if we could have a big enough triangle and measure the angles of that triangle, we could determine if our universe is flat or not. In a flat, three-dimensional universe, light rays travel in straight lines, and a large enough triangle will still add up to 180 degrees. What is amazing is in the last while, we've been able to use the most important observation in cosmology to determine a triangle and measure the geometry of the universe. This observation is the cosmic microwave background radiation, the afterglow of the Big Bang. And I'd spend more time on it if I wasn't trying to get somewhere else. And let me just give you a quick summary. When we look out, well, you know, the universe is 13.72 billion years old, except in many states in the United States. But it's 13.72 billion years old, and that means if you look out far enough, you should see the Big Bang. And in principle, you could. But between you and the Big Bang, there's a wall, however. We can't see all the way the Big Bang, just like I can't see across the street because this wall is opaque. When I look back in time, I'm looking at the early universe earlier and earlier. And that means that I'm doing cosmic archaeology. As I said, when I look at stuff a billion light years away, it's a billion years old. But the universe was denser and hotter at earlier times. And when the universe was 100,000 years old, it was so dense and hot, 3,000 degrees, that matter was no longer neutral. Hydrogen, the dominant stuff in the universe, was knocked apart by radiation. And it formed what's called a plasma. And a plasma is opaque to radiation, and therefore you can't see through it. So if we try and look past this plasma, we can't see through it. But when the universe became neutral, just as I can see that wall because the light reflects from the lights on the surface of the wall and comes to me because the air is transparent, the radiation at that moment when the universe became transparent from that hot plasma could come all the way to me and of course cool down in the interim, and I would expect to see it not at 3,000 degrees, but at 2 or 3 degrees above absolute zero, and that was what was discovered by accident in New Jersey in 1965, of all places, by two people who didn't know what they were doing, but won the Nobel Prize. And so that's great, but the point is, on this surface, when there's a very important scale, 1 degree, because this surface occurred when the universe was about 100,000 years old, and this distance here represents 100,000 light years. And this means Einstein tells us that no information can propagate faster than the speed of light, and this means nothing that happened over here at that time could affect anything over there. But more importantly, it means if you're a lump of matter, and you're on the scale, well, what happens? You start to collapse due to gravity, and then pressure heats up, and all sorts of things happen. But if you're a lump that's this big across, you don't even know you're a lump, because gravity can't propagate across you. So you don't know you're supposed to collapse. I used to watch The Roadrunner when I was a kid, and Wile E. Coyote would run off a cliff, and then only eventually should he realize that he was supposed to fall. And that's what happens here. So the largest clumps that will have started to collapse at that time will be 1 degree across, or so. And that's a triangle, because you see, it's a triangle with 100,000 light year across line there, a known distance away from us, and in a flat universe where light rays travel in straight lines, that will subtend on your eye, that 100,000 light year across ruler, 1 degree. But in an open universe where light rays diverge as you go back in time, it'll subtend a smaller angle, because light rays have diverged, they come back. So this angle. In a closed universe, it'll be a larger angle. So all we have to do is actually image that microwave background and look for lumps, and ask, are the biggest lumps of 1 degree, half a degree, or 2 degrees, and causality basically will tell us the geometry of the universe. And that's what we've been able to do, and the first experiment to do that was what it's typical, it's good to talk about in Australia, it's called the boomerang experiment. And it was a microwave radiometer and a balloon that went around the world, which is easy to do in Antarctica. At the South Pole, it's really easy. But in this case, it was from McMurdo. It took 2 weeks to go around. It came back to where it began, which is why it's called boomerang. And this is an image that superposed on the original one. This is a false color image of the microwave background taken from by that microwave radiometer. And here are the hot spots and cold spots, lumps in that primordial universe, which later on would collapse to form stars and galaxies and people and aliens and all the rest. And the question is, how big are they? So we can, on a computer, of course, we can model universes, a closed universe, a flat universe, an open universe, and ask how big on average, 100,000 light year across lumps would look. And in a closed universe, they'd be this big, but these are bigger than these lumps. In an open universe, they're about this big on average, and these are smaller than these lumps. But in a flat universe, it's just like Goldilocks. It's just right. And we now know to a 1% accuracy that the universe is flat, as we knew. But we were totally wrong about why, because in fact, there's a problem here. I've just proved to you the universe is open now. I've proved it's flat. There's 30% of the amount of mass in the universe needed to make it flat. That must mean we're missing 70% of the stuff. Well, where could it be if it isn't around galaxies and clusters? It could be where the galaxies and clusters aren't. What is where the galaxies and clusters aren't? Nothing. Well, that's okay. If nothing weighs something, then we're okay. And, well, the problem is, in general relativity, if nothing weighs something, which is possible, it's gravitationally repulsive. It's not attractive. It's anti-gravity. You put energy in empty space and it's gravitationally repulsive. So if you wanted to look at the expansion of the universe, and this is what observers were doing, they were trying to measure how fast the universe was slowing down in 1998. And they were looking at objects called supernovae, which I don't have time to go into, further and further distances to measure the distance versus velocity to see if the universe was slowing down. What they discovered, and here is an image from back then. Here is the expansion rate of the universe, distance versus velocity, basically. And in order to guide the eye, if you draw a straight line through this data set and bring it down here and make the straight line horizontal, a decelerating universe, which is what everyone expected, almost everyone, to detect, except for me, It was this here. The supernovas should have lay along here, but in fact they didn't. On average, they laid above the straight line, and that means, in principle, the universe is accelerating. The expansion of the universe is accelerating. Exactly what you'd expect if you had energy in empty space. Just for fun, if you ask how much you need to fit the data, you need exactly what we were missing. So everything is consistent with a universe dominated by the energy of empty space. 70% of the energy of the universe resides in empty space. We don't have the slightest idea why it's there. If anyone tells you they do, they're lying, especially if they're a string theorist. And, but we do think its existence is probably tied to the beginning of the universe, which is why people like me are interested in it. But it will determine our future, and that's what I want to spend the rest of the time talking about. A little bit about some of the implications it has for determining our future, and some of the thoughts that have come up that have spurred a bunch of us to think about the future of computation in life. The first person to think about this, of course, was Yogi Berra, an American philosopher, who said the future ain't what it used to be. So let me tell you some of that. And the future is miserable. Okay. So the first person to really discuss this was George Orwell, who said, to see what is in front of one's nose requires a constant struggle. And of course, this is what he meant by this, if I can, let's see, there we go. Okay, that's what he meant. And what he meant, of course, was that if you have a universe dominated by empty space, it will continue to accelerate, and that means it will grow in size exponentially. It doesn't matter if you don't understand these equations. It will grow in size exponentially. It'll get bigger and bigger and bigger. What does that mean operationally? It means objects, this means velocity. The velocity of objects will be proportional to the distance away from us until a certain distance, beyond which objects will be moving away from us faster than the speed of light. That is allowed in general relativity. Objects can't move through space faster than the speed of light, but space can do whatever the hell it wants. And space can carry objects away from you faster than the speed of light. When that happens, they are invisible. So since objects are moving away from us now, as they get to larger and larger distances and longer times, they'll be moving faster and faster and faster, and eventually everything will disappear from our view. And the effects will soon be visible, because if you plug in the numbers, the distance at which objects are receding faster than the speed of light is about 18 billion light years away from us. The universe is 14 billion years older, so these effects should become dramatically visible soon. And in fact, it's a little bit different than you think. They don't just twinkle out of existence. What happens is they're moving away faster and faster and faster. As they're moving away faster and faster and faster, the light from these objects gets what's called redshift. It gets stretched out. And I think I'll skip over this quickly, but it turns out in 150 billion years, which may seem like a long time to some of you, it's in a cosmic sense, it's a blink of an eye. All objects now will have their light shifted by a factor of 1,000 compared to what it is now. And that means all the visible light will disappear, but of course, X-rays and other light will be visible. But you don't have to wait very long. In 2 trillion years, the redshift of all objects outside of our local supercluster will exceed a factor of 10 to the 53. The wavelength of all light from all objects outside of our local cluster of galaxies, which will by then have merged into one galaxy, will be the wavelength will be larger than the size of the visible universe. They'll be invisible. The rest of the universe will have disappeared. And I think I'll skip this part. Doesn't matter. I've used the fact, by the way, so the longer we wait, the less we'll see in such a universe. That's one of the reasons it's miserable. Because an unexamined life is not worth living. And without being able to see the rest of the universe, we won't know what's going on. So I've argued, in fact, that you should fund cosmology now while we have a chance. I've argued that to Congress people, but 2 trillion years is a impedance mismatch of 2 years, which is the long-term future for a congressperson in the United States. So that's now. But in any case, so that's the first thing. The universe is going to disappear. Next thing, I want to spend. Oh, good. I'll end a little early, and then I'll probably give me time for questions. That's good. Well, we'll see. So I want to now. This motivated me and a colleague of mine to think about things, and in fact enter into a great debate with my good friend Freeman Dyson. Freeman Dyson is an eternal optimist. It's been very good to him, and he has argued that life could exist forever in an eternally expanding universe. It's the only universe in which you think you might be able to have the hope of living forever. And so the claim, however, we made is that he's wrong. Is that, in fact, the worst universe is one that's expanding exponentially, but in fact, it even is caused us to realize that in any universe, life cannot exist forever. And I want to explain why, and it's based, believe it or not, on computation, among others. Well, something like computation. So here's what Freeman Dyson said. What does it mean to live forever? Now we're becoming more kind of singularity-like in AI, so we're back to where we're. So assume that life is consciousness, which is information processing. Okay, consciousness is information processing, nothing more. Maybe it's more, but it's at least information processing. Okay? Then he said, well, let's assume that life is independent of any specific metabolism. We're not going to worry about little things like the sun dying or decaying of protons. You could form life from electron-positron pairs or something. So we won't worry about these little demises. Okay? It's like, or the loss of energy. It's like, in Star Trek, which I'm contractually obliged to always mention, there's always some civilization that is dying and losing its energy, and they put their consciousness in a computer, and Kirk, unplugs it or something. But anyway, so we're not going to worry about that stuff. Okay? As I say, Dyson was an optimist. And here's what he said, here's what he defined by living forever. Living forever is having an infinite number of thoughts. If a civilization could generate an infinite number of thoughts, it's live forever. And so the subjective time, which is what we're going to measure, is a total number of thoughts. And the question he asked is, can a civilization have an infinite number of thoughts? And he was no fool, so he started to ask whether you can do this. And to live forever, since computing and information processing in general costs energy, it's a problem. So he just pointed out that the free energy used to process information is proportional to the amount of information and all to the system's temperature. And he defined a quantity called the quality of life, Q, which is the rate of information processing, bits per second. And he estimated, and this is a wild estimate, and the people here, AI people, will probably have a much better estimate than I would, that let's say humans for this rate is 10 to the 23 bits per second. As he said, it's the amount of information need to be processed in order to say in 1 second, cogito ergo sum. I think, therefore I am. And understand what that means. And so it's some number. I don't care whether it's 10 to the 23 bits per second or some other number. It's a number. And the idea is you can't be conscious until you have that rate of complexity. And so it's my Mac is not there, but maybe it one day will. And that's the question of the singularity in some sense. When do you get to this key point of information processing where you can be conscious? Okay, so the question is, can the total amount of information a civilization processes in the infinite time diverge, but the free energy converge? Because it turns out we only have access to a finite amount of energy, even in an infinitely long-lived universe. I should have put that in there, but that's something we've actually shown. So we have a finite amount of energy. Can you live on it forever? And Dyson said, well, in principle, yeah, but let's see, there's a problem. Life forms have to cool, it turns out, because it turns out the amount of energy you're dissipating depends on the system's temperature. So life forms have to cool as they process information if you want that integral of the total rate of information processing integrated over time to be infinite. And I don't think I put the equations for this group. I could have, but I didn't. But you could also show that life forms, as Freeman Dyson showed, that life forms can't cool fast enough. So you cannot, eventually, the complexity, if life forms are continually operating, in order to have an infinite amount of thoughts with a finite amount of free energy, they have to cool, but they can't cool fast enough. And so eventually, the only way that integral of the free energy can be finite is if the complexity goes to zero over time. The quality of information, the quality factor. But that means you lose consciousness. So that means you can't be conscious and have a civilization that's conscious forever. Now, a lesser man would have given up then, but Freeman isn't a lesser man. So he said, well, there's a simple solution to this. All academics know about the solution: hibernation. So the idea is that if you're thinking and you have some complexity, you're processing bits per second while you're awake, but let's just imagine you could go to sleep and then not process any information whatsoever. Then he showed, if your period of inactivity increases as the universe expands in a well-defined way, then you could show that the fraction of time you're awake is an increasingly decreasing function of time. So the idea is you sleep, you wake up, you have a thought. You sleep longer, you wake up, you have another thought. You sleep longer still, you wake up, you have another thought. It turns out the fraction of time you're awake is decreasing, but the subjective number of thoughts is an increasing function of time, and therefore you solve the problem. You can have an infinite number of thoughts, you just sleep longer and longer. If you could achieve this. Whether you could achieve that is a different question. Now, the question is this possible? And there are two answers to this question: yes and no. Freeman's answer was yes, and our answer is no. What is amazing is, the answer comes from the question of whether life is quantum mechanical, which is the reason I'm fascinated by it. Well, I did it, so I'm fascinated by it. But it turns out the question of whether you can do that comes down to the question of whether life is quantum mechanical. Because, in fact, ultimately, quantum mechanics governs everything. And if quantum mechanics does govern life and information processing, then we argued that there must be an end. And the argument goes as following. Well, it was pointed out that there's such a thing as reversible computation, where you can actually do a computation and not dissipate any energy, which is great. And quantum computers are one way of, in principle, doing that. But that's not where you dissipate energy. If you repeat the same computation over and over again, you can do it ad infinitum without dissipating energy. So you can stare at your navel and go forever. But if you want to have new thoughts, you have to erase the registers and think again. And erasing the registers is where you dissipate energy. When you erase the registers, you dissipate kT of energy. And so if you want to have a series of new thoughts, you erase the kT of energy. Okay, but here's the problem. Therefore, that means when you do a new computation, you will have dissipated energy. But quantum mechanics tells us that any finite size system has a finite number of states below so the ground state is not what's called an accumulation point. Namely, if you take the lowest energy state of the system and you go a finite amount above it, there are always a finite number of levels below you for any finite-sized quantum mechanical system. And that means, okay, so here's the system. It's a civilization, it's a computer, it's whatever you want. You do a computation and then you erase the registers. You drop down a quantum state. Then you erase the registers again after doing another computation, drop down, drop down, drop down, drop down, and eventually you end up at the ground state. Once you're at the ground state, you can't do anything. There's no accessible energy left. So we argued that, to Freeman, that therefore, if life is quantum mechanical, computation must end. Life must end. Consciousness must end. And he agreed with that, because it's right. But Freeman said, well, why does life have to be quantum mechanical? Can you avoid the quantum mechanical limit? And one way, and how do you avoid the quantum mechanical limit? Well, we don't behave quantum mechanically because the energy levels in our body, the quantum states, are very small compared to the accessible energy in our body, so we behave quite classically. It's one of the problems with quantum computers, in fact. Large objects tend to behave classically. So if you could arrange a system where the energy level spacing got smaller faster than the energy loss, then you'd always be classical. And he even gave such a system because he read science fiction. He read The Black Cloud of Fred Hoyle, which many of you read. The Fred Hoyle, have you read that? It's a great science fiction novel about a cloud in space of particles, and the information processing in those particles was actually based on their motion of the gas. And if you allow such a system to expand, Freeman showed, then the states squeeze enough so the system can always remain classical. And therefore you can avoid the quantum mechanical limit, and you might appear to avoid this problem. However, it turns out that as the system gets more and more diffuse, you can't communicate between the particles of the system. Electromagnetic radiation will get out of the system, and that's the level of the debate right now between us and Freeman. The question is, can life avoid the quantum mechanical limit? And so, or as Freeman would have put it, and did put it, will life be analog or digital? If life is digital, then the end is near. A few hundred gazillion years from now. Digital being quantum mechanical. If the discreteness of the energy levels of a quantum system become important, then it's over. So the idea is get rid of the iPods, go back to LPs, and that's the future. But what's fascinating to me about this whole argument is, and I hoped it would be fascinating for you, is that what is really amazing is that it comes down to quantum mechanics. If quantum mechanics ultimately governs a universe starved of energy, consciousness must end for an eternally expanding universe. Now, what I really love about this is that it's all physics. I didn't even mention what life is, or what consciousness is, or what metabolism is. And that's the great thing about physics. You don't have to know anything to do a lot. And so, it's not, the future of life is not biological, it's physics. And some simple physics arguments tell you that what the ultimate limit on consciousness really is. So that's part of that I want to talk about. I also want to mention something that I told you I'd mentioned Moore's Law, and here it is. Cosmology gives a limit to Moore's Law, which fascinated me when we first realized this. Okay, let's see. To determine, if we want to use the resources available to us in the universe to compute, we have to get them. So we have to be like the Borg. So we go out, this is what's called it doesn't really matter what this is, a conformal diagram, but what we do is we travel out to nearby stars, we vaporize them, and we transport all the energy back to the Earth. Okay? That's the best you can do, is to harness all the energy in a sphere expanding at the speed of light and send it back. And it turns out you can actually do a calculation. You can ask, how much energy can you get that way? And you can do it. We did it. The number turns out to be rather interesting. The total energy that we can get in an infinite amount of time in an expanding universe turns out to be 3 times 10 to the 67 joules of energy, which happens to be about the total mass within today's visible horizon of this is assuming the universe is exponentially expanding, by the way. With the total mass of protons and neutrons within our horizon. So we take all the stars and all the baryons and everything, and we vaporize them, come back to Earth. That's the total amount of energy we get. But there's a problem. In a universe where we have an energy of empty space, there's something called a Hawking temperature. And it's a very low temperature, like 10 to the minus 47 degrees Kelvin or something. But it is known that to process information down a noisy channel requires error correction, and the error correction takes energy. KT of energy, it turns out. So all you have to do, since you can never cool the universe below the Hawking temperature, you could just take the total energy accessible to us and divide by KT, where T is the Hawking temperature, and you get the total number of information that can be processed in the future history of the universe. It's 10 to the 120 bits. That gives a limit on the amount of information that can be processed in the future in a universe dominated by the energy of empty space. Now, if you plug Moore's Law into this, you'll find out you will utilize all of the, you will process all of the available bits in a time less than 400 years. This is not giggy years or billions and billions of 400 years. Now, of course, Moore's Law will probably come to limits before that. But I find this fascinating, is that cosmology tells you a civilization cannot continue to improve exponentially its information processing for a time that's billions and billions of years long. When people talk about civilizations that last billions of years, they're not living as we are now, where our computers are doubling every 12 months. It's actually, the number is really actually about 250, because 400 years means when you go out, that means if you can harvest all the information in the available horizon. But of course, you can't. In 400 years, you can only go 400 light years. And so when you ask how much information is available, or energy is available in 400 light years, and you get a much smaller number. So it turns out to be about 250 years when things converge. So centuries is a time that cosmology puts a limit on Moore's law, and I thought some of you might find that interesting. But it doesn't matter, because we may not know, in the end, we may not need to know anything. And I'll end with a few little bits that will, that's the optimistic part of the talk, so let me get to the really pessimistic part. So one of the things that's weird about the universe is this fact that I told you that, well, here's a brief history of time. This is the energy density of matter in the universe. It goes down as 1 over the volume. Okay? This is the energy density of empty space that remains constant, and we apparently live now when the energy density of empty space is 3 times bigger than the energy density of everything else. But if you look at this, it should cause you some consternation. It causes physicists consternation. Because in fact, we are living very close to the only time in the history of the universe when these two quantities are the same. Why should the energy of empty space be within a factor of 3 of the energy of everything else? In much earlier times, it was much smaller, and much later times, it'll be much bigger. We're living the only time in the history of the universe when they're about the same. But Copernicus told us we shouldn't be that thing. There's nothing special about when we live. So why are we living in such a special time? Well, the argument has been given that galaxies exist. What does that have to do with anything? Well, let's say the energy of empty space were 50 times bigger. Then these two curves would cross, not today, but that time. What's that time? That's the time galaxies first formed, when the universe was about 1 billion years old. But the energy of empty space is gravitationally repulsive, I told you. So if it began to dominate before galaxies first formed, galaxies wouldn't form, because the repulsive expansion would beat the attraction. So some people have made the following argument. Maybe that's telling us something. And it's led to something that I call anthropic mania. But the idea is, let's say there are many different universes, and the energy of empty space can vary in each one, then only those in which it's not much greater than what we measure today will galaxies form, and only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because astronomers are here to measure it. Which sounds like it's a tautology or some religious statement or something, but it's neither. It may be true. It's an awful possibility, because it says one of the fundamental quantities in nature, the energy of empty space, is just an environmental accident. It's like the Earth-Sun distance. There's nothing fundamental about that, but if the Earth-Sun distance were any different, we wouldn't be here. So it's really saying, it's kind of cosmic evolution if you want. It's really saying natural selection. We would not expect to find ourselves living in a universe in which we couldn't live. It'd be a big surprise. And so it may say that this fundamental quantity is just an accident. But it turns out, and I won't go into it, that in fact, well, particle physicists are way ahead of cosmologists, because there's one number that they don't understand, but particle physicists haven't understood many more numbers for much longer. And the argument is, well, maybe every fundamental constant in nature is just anthropically determined. Namely, if it were slightly different, we wouldn't be here. But if that's the case, there's no fundamental laws of physics. If physics becomes an environmental science, God forbid. And that means that there's no fundamental theory. It's all just an accident. So maybe there's no point to understanding the fundamental structure of the universe, because there is no fundamental structure of the universe. There are many universes, and in each one the laws of physics are different, and etc. And if you want to, and actually my new book, which is coming out in January, A Universe or Nothing, it talks about that a lot more. Okay, but now let me end by telling you something that should make you maybe feel a little bit better. Because, it'll make you feel better about the present because the future is so bad. Recall, I almost said it, but I didn't at the beginning of the talk, which I kind of meant. I told you we know the universe is expanding, but we didn't always know the universe was expanding. In 1900 and 1915, in fact, when Einstein first developed general relativity, he didn't know the universe was expanding. He thought the universe was static. That was the conventional wisdom in science. In fact, a guy named de Sitter even came up with a description of a static universe with one galaxy, surrounded by eternal space. And the question is, what will the universe bring, the future bring? What will physicists, whether they're AI physicists or real or human or biological physicists, on stars, on planets that develop around stars billions of years from now. What will they determine will be the universe in which they live? And the amazing thing is, those scientists in the far future will do the best science they can possibly come up with, building the best instruments. They'll develop general relativity, they'll develop electromagnetism, quantum mechanics, they'll do everything, and they'll come up with completely the wrong answer. They will, in fact, imagine that they live in an island universe surrounded by empty space that isn't expanding, which is exactly what we thought we lived in 1900. And the reasons are quite simple. What are the three reasons we know there's a Big Bang? First, the Hubble expansion. The fact that galaxies are moving away from us. But I've just told you, in a few 100 billion years, we won't have any galaxies left to observe that are moving away from us. So there'll be no observed Hubble expansion. Astronomers will look out and see no galaxies that are moving away from us. In fact, all evidence for dark energy will disappear, because the only time that even though, by the way, at this time, the dark energy to matter ratio will be huge. There'll be a million times more dark energy than there is matter, but it'll be invisible. Because the only time it's visible is now. Because at much earlier times in the universe, when the energy density of dark energy was much less than the energy density of matter, it was gravitationally irrelevant. So it could never have been detected. At much later times, it's pushed everything outside the horizon. So the only time you can measure dark energy is now. And then you say, what about the cosmic microwave background radiation that gave us evidence for Big Bang, these beautiful pictures of the early universe? Well, the answer is it goes away too. First of all, it gets redshifted, and the peak moves to different frequencies, as does its intensity. So when the universe is 100 billion years old, the intensity would be down by a factor of a million. But you can imagine experimentalists are a million times smarter. That's easy if you've ever met an experimentalist. But the problem is there are free electrons in our galaxy, and that means there's a plasma frequency. That I told you, in a plasma, radiation can't get through. And you can ask, what's the plasma frequency of our galaxy? And it's 1 kilohertz. And when the universe is 50 times its present age, the microwave background frequency will be below the plasma frequency, so it won't even make it into the galaxy. So you can build the best detector you want, you won't see it. So it's 2 out of 3. The third bit of evidence there was a Big Bang happens to be the abundance of light elements. The fact that 24% of the universe is helium tells us there was a Big Bang. But stars make helium. So now, at the beginning of time, 24% of the universe was helium. Now maybe 28%, because stars made a little bit. But in 1 trillion years, 60% of the universe will be helium, because stars will have produced helium. For observers 1 trillion years from now, there'll be no need for the Big Bang to make helium. Stars will have been able to make it. So that all of the 3 bits of evidence that tell us there was a Big Bang will have gone. And observers, as I say, the most rational conclusion from observing a single galaxy, which is the galaxy in which they live, surrounded by empty space, is that they live in a universe in which there's a single galaxy surrounded by empty space that's static and will go eternally into the future. So it'll be a return. I find it very poetic. It'll be a return to the wrong picture that we had 100 years ago. And in fact, being the eternal optimist that I am, as we put it, the good news is we live in a very special time. The only time when we can observationally verify that we live in a very special time. And that's facetious. What I mean by that is, of course, quite the opposite. We have to realize that we have this weird cockamamie universe dominated by dark energy, and it all fits together, and the Big Bang really did happen. But before we conclude that we know everything, we should realize we're living at a particular time in the history of the universe. There may be observables we could have seen 5 billion years ago that we can't see now. There may be observables 100 billion years in the future that will dramatically change our ultimate conclusions about the future of the universe, which is one of the reasons why I'm so suspicious of predictions of the future. We don't have all the data. So all I can say is, in the future, we will be lonely and ignorant, but dominant. And those of us who live in the United States are really quite used to that. Thank you. Thank you very much.
We've got time for some questions.
I threw a lot out there, so maybe there are a few questions. Yeah?
What's happening to time? Will time be expanding with it as well?
No. The nice thing is that the great thing about general relativity is you can be going at the speed of light and still be standing still. And that's what's happening. You're doing it right now. Depending, because, you know, you weren't standing still here unless you had a lot of coffee. But relative to the sun, we're not moving very fast, but relative to an audience at a Singularity Summit on the other side of the universe, we're moving away at the speed of light. Because we're at rest in our local space, so we're at rest and they're at rest, the space between us is expanding. And as long as we're all at rest in our local space, our clocks are ticking all at the same time, at the same rate. So time doesn't dilate at all for local observers.
Hugo?
Do you think the laws of physics of the universe is designed?
Was that?
Designed?
Do I think the laws of physics are designed? Absolutely not. There's no evidence for that whatsoever. The picture I gave, even the anthropic picture, is just like evolution. Evolution gives the appearance of design. Bees can detect colors of flowers so they can get honey, and all the rest. They can make honey. But the point is, they weren't designed to do it. They were rather, if they couldn't do it, they wouldn't survive. So in fact, natural selection gives a perfectly beautiful mechanism of producing an Earth that looks like it was designed for life. Similarly, the universe may look like it's designed for us, but it's just a statement that if it wasn't, we wouldn't be here to enjoy the fruits of the universe. And so it's not surprising, as I say, that we live in a universe in which we can live. So there's no evidence in anything I know of that for any design in nature. In fact, quite the opposite. The universe behaves as if there's no design. And that doesn't mean it wasn't designed. It just means there's no evidence of purpose in the universe. And since I find the plausibility of purpose highly implausible, I would argue that it's extremely unlikely. Okay?
The hyper-intelligences that we might be building in a century or so, if they get smart enough, they're like a trillion times above us, would they be smart enough to not just do what Dyson's doing and, no, it's good, MIT, good calculating how to build a baby universe, wouldn't they actually do it? If that's possible, could it have been done in the past?
It could have been done in the past. If we could create a baby universe, we probably can't. The laws of physics probably preclude that. But I noticed you're dozing during the part where I argued they won't get a trillion times smarter, I don't think, because Moore's law will only take us 200 years into the future. But it's possible, it's certainly possible that well, in fact, let me come on your side here and say, here's how life can exist forever. We can't exist forever in our own universe because of the law of the constraints I gave. But what we might be able to do if we could create a baby universe is create a baby universe, but just before it became causally disconnected, as it will when it collapses to form a black hole in our universe. We drop some DNA down it, and we just hope that life evolves in that universe. And then they do the same thing. So that's a way in which you could hope to propagate forever by constantly creating baby universes. And if that's the kind of design that you mean, that's certainly possible. It's certainly possible that a universe was, if you could create universes, that you could create a universe in which eventually life would evolve. But that's not what I mean by purpose, or I think what most people mean by purpose. But the answer to your question is right now is there's no evidence that we can create baby universes. In fact, all of the evidence from quantum field theory is that you can't create baby universes. But that's an open question at the forefront of physics, so I can't give you an answer one way or the other. Up there, yeah.
Arthur C. Clarke once, I think it was Arthur C. Clarke, said that our purpose is to reboot the universe.
Yeah, but Arthur C. Yeah, well, okay, maybe it is, but I think that's incredibly pompous, and like most things that Arthur C. Clarke said as he got older, they were pretty silly. I mean, he had really ridiculous ideas about physics by the time later on. And that's not to put down the wonderful stories he wrote, but I suspect that to assume that we can control the universe or that the universe exists for us is incredibly myopic. And if anything, in fact, I think I have it here. Remember, the three things I want you to remember is that you are cosmically completely insignificant. We could take all of the stars, all the galaxies, everything we can see today accounts for 1% bit of pollution in a universe that's dominated by dark matter, dark energy. So get rid of everything that defines the universe for us. Everything that's beautiful in the night sky, the stars, the galaxies, the aliens, everything, the universe is largely the same. So we are completely insignificant in a cosmic sense. Life and all the matter in which life is based, protons and neutrons, are cosmically insignificant. The universe would be essentially exactly the same if we did away with all of it. So you're more insignificant than you thought.
And do you Big Bang?
What was that?
Did you ever think of the recipe for a...
Well, that's what he's talking about, a baby universe. And the answer is there's no evidence we can do that. As I say, the future is miserable. The universe may be an environmental accident, and cosmology may ultimately limit the knowledge that we can gain about nature, and whether we like it or not. And I think that's what I want to remember. Oh, so I think I didn't want you to all to go out and commit suicide. So I said, enjoy your brief moment in the sun, which is really what we have. We have a brief moment to try and understand it. I don't think it's much longer than a brief moment. I'm having a good time trying to understand it, and that's good enough for me. Maybe that's a good way to end? Yeah, it's 9:30. Thank you.